Good. How are you? Everything is fine? Okay. So, today we move forward with rainfall runoff modeling, and today we will start dealing with a couple of basic rainfall runoff models. I remind you, rainfall runoff models are mathematical models that allows us to express, to compute, to estimate the river flow depending on input data, including rainfall, which is in many applications the most important one, and for this reason they are called rainfall runoff models. Input data may include also other variables like temperature and water storage in the catchment, etc. And as I said, today we will introduce two basic rainfall runoff models with the aim to provide a first example, very classical example. Today I am introducing two models that can be considered part of the history of hydrology, let's say, and still they are used in some practical applications. But they are very important for me because they introduce, being simple models, they allow me to introduce some basic concepts. And then starting from these very simple models, we can include more details and make the representation more complicated, more detailed, let's say. So these are the basis. And what I'm doing today is, for this reason, important. It's a bit, you will see, complicated mathematically, but not much. I will use the slides to support my lecture, but then I will basically rewrite and rederive what is shown in the slide at the blackboard. And today's lecture is providing many subjects, many questions that I may ask at the exam. So if you have some doubts on what I'm doing today and you are in doubt of what I could specifically ask at the exam, you can ask me and for more details. Okay, let me clean the blackboard because I forgot to do that before, and then we can start. I also wonder whether it's helpful to turn on the light here. I will try to do that. Okay, since some time passed from my last lecture, I just would like to remind you some basic concepts. And I will use the slide for this. Let me see. Basically, I just would like to remind you some basic concepts. I introduced the Reynolds transport theorem just to introduce the concept that we will use energy balance and mass balance to write the equations that form our models, our rainfall runoff models. So I just said this is a general expression of a balance equation. We will apply this balance equation in a very simple way. What we will use is much simpler than this integral presented here. But I will use this conservation equation, which is complicated here because it's expressed in general form, to compute mass and energy balance. This is basically the concept. These are basically the concepts on which our models are based on. So mass and energy balance. But when I went forward, I said that our control volume is the catchment. So we will apply energy and mass balance to the catchment. And then I introduced a classification. Then you remember these slides. I talked about hydrograph, phyetograph, and I provided some basic definition like what is a catchment, what is the river flow, what is the cross river section, and then I said what is the concentration time. So don't forget these concepts. And then I introduced this classification, which may seem a bit boring because you may see it like you know, just a very boring classification of different models, but I think it is important, and I explain you why. Keep in mind the second classification, which is black box versus conceptual versus physically based. And I just would like to provide more details. I said that our basic equations are balance equation, energy and mass balance. These are physical equations. These are laws of physics. And they are extremely useful to write our models if we want to write a so-called physically based model. So if you want to use the law of physics to write our model, to develop our model, then we have to use mass and energy balance equations, and the model is called physically based for obvious reasons, because I'm using the law of physics to base it, to set the basis for it. So the model is called physically based, but it's not compulsory to use these balance equations to write the model. This is what I would like to stress. I said that we can use balance equation, mass balance and energy balance, to develop a Rainfall-Runoff model, but we are not obliged. We could also try to establish a purely empirical relationship between rainfall and runoff without caring of mass and energy balance. This is possible. If you have data, you can just look for a relationship, a causal relationship, or causal, I don't know how to pronounce it correctly. I mean a deterministic relationship between runoff and rainfall. This is fine. In this case, you are not using the law of physics to set the basis for your model. You are using an empirical equation, and the model is called black box. So this is the important concept that I wanted to highlight before starting. You can decide to use the laws of physics, or you can decide to use an empirical equation. And the difference is that the former is a physically based model, the latter is a black box model. In between, you have the conceptual models. Because you may use the law of physics, but you could simplify it to make them simpler, and you can simplify them in an empirical way. So you can stay in between. And the model is conceptual. This classification is not black-white. Sometimes we have models for which it's not so clear if they are physically based or they are empirical. So take this classification as a kind of fuzzy classification. Still, it is extremely useful to get oriented in the number of models that you have available to perform the rainfall-runoff transformation. Keep in mind that if you have this need to express runoff depending on rainfall, the literature proposes to use several solutions. I would say tens, probably more than tens, for sure 40, 50 models, but probably more. And therefore it's important to get oriented, to understand why in one case you select model A and in another case you select model B. So to get oriented, when several models are available, you need to know the models, of course, their peculiar behaviors, and you have to know how to classify them. And if you have the question, but how can I select between a model or another, the answer is depending on your needs. So if your needs is very practical, I have to design a bridge, you may use one model. If your need is scientific, I want to understand what's going on, then it's better to use another kind of model. And also, your data availability is important. If you have a lot of data, then you can use one model. If you have a few data only, it's better to use another type of model. We will learn the basics of model identification. This process of selecting the most appropriate model is called model identification. We will learn the basis, but for now it's important that you know that you have many possible solutions, and the selection between one or another is given by basically, let's say, the context, your needs, your data availability, your purpose, your main purpose, and sometimes, of course, there are more than one possible solutions. Now, let's look at the third classification, event-based versus continuous simulation. I already explained to you that event-based models typically simulate a given event only. Typically, it's a flood event. The continuous simulation model, they instead run for years, or let's say months, long periods, or maybe 1,000 years, it's possible. And in this course, we are mainly interested in the generation of synthetic data. So our main interest is for continuous models. But it's important to know that you may also consider the opportunity of using an event-based model. For instance, if you have to manage a drought, a water shortage, a period of water shortage, you may be interested in simulating river flows only for that period, not for the whole year, for instance. The advantage of using an event-based model is that generally it takes less computational efforts for obvious reasons, because the simulation is shorter, and also the model usually is simpler. Why that? Because when you simulate a drought, for instance, a water shortage, you are interested in simulating the hydrological processes that govern the droughts only. You are not interested in simulating floods. But if you perform a simulation for a whole year, then you have to reproduce everything, because you may have a flood, you may have a drought, and therefore, of course, the model is more complicated. So keep in mind this classification also. This very important difference. When you see a rainfall runoff model, you should ask yourselves soon, this is a continuous simulation model or it's an event-based model, because it changes completely. It's a different model. And also black box versus physically based is useful because it allows you to better understand what you can get from the model. Okay. So now let's move forward then, because I said that I want to introduce some models. And let me start with the first rainfall runoff model that people devised, almost involuntarily, I would say. And this is the rational formula. Let me see if I can succeed in getting the light on. I am concerned. Probably they are here. I don't want to turn off the projector, otherwise it's. I can see. Do you see the switch? I don't see any switch because I don't usually teach in this room, so they are not here.
Maybe it's there.
Where?
Back the black.
You mean in the box?
Yes, near. Yes. No.
No. Ah, okay, fine. No, this is the microphone. Or okay, I think. I can do even because I think it's visible, but I just wanted to see. I think it's here. So, okay. Okay, fine, no problem. Let's wait for getting it back. Okay, it's coming back. Okay, let's. Okay, fine. I finally was successful. Sorry for that. And it's coming back. Just wait a couple of minutes, but I need the blackboard now, so it's not a problem. So I said the rational formula was the first rainfall runoff model. Some people say that it was proposed in 1859, and some people say that it was proposed later, like, I don't remember well, I think 1872. The reason why they debate is that the rational formula was proposed independently by two researchers. One was British and one was Irish. So you know that British people and Irish people, they don't get along very well. So they debate on who was the first one that proposed it. We don't care about that. And the rational formula is also called the CIA formula. You will see why. And the reason why it's called CIA is that it's easier to remember, because CIA also recalls the shape of the formula. You see that is CIA. So it helps you, because you may refer to the CIA of the United States, and then you may remember well the rational formula. So why the rational formula was developed? Because people needed to provide a reply to a very important question. What is the peak flow for a river? So this was the motivation why people set up the rational formula. So basically, this is a very simple rainfall runoff model, which is an event-based model, because it only provides an estimate for the peak flow. It's not very useful for us, but it's important for us because it helps to better understand what's going on. And basically, the rational formula is very simple. It says that the peak flow, so let me see if I put the P here. Yeah, you see QP, which means peak. QP is equal to the product of C times I times A. And okay, I in the slide is lowercase, so let me use the lowercase. So let's focus on the multipliers. C is called runoff coefficient, and basically it takes into account water losses. And let me provide more refined, more details later when I have introduced all the other multipliers. I, is rainfall intensity. So C is adimensional. The rainfall intensity is expressed, the units are a length over time. So the rainfall intensity, usually it is expressed like in millimeters per hours or millimeters per day. It depends on the time step. It's a length over time, where the length is the rainfall depth. Okay? So let's say that it's L over T, length over time. And then A is the catchment area. And the catchment area is expressed as a length square. So basically, if you see length over time, adimensional, length over time, length square, the result is length cube over time, which is volume per unit time, river flow. And basically, the concept is very simple. People thought that the peak flow is proportional to the rainfall intensity. If you have an higher rainfall, you have an higher peak flow. This is very intuitive. And therefore they thought to express the peak flow as the product of what? Rainfall intensity times the area of the catchment, which means volume of rainfall over time. Okay, because if you multiply the rainfall depth by the area of the catchment, you get a volume of rainfall. You get the volume of rainfall over the catchment. If you divide it for the time step, you get a volume of rainfall over time. So basically they thought that the river flow is just equal to the volume of rainfall that falls over the catchment divided by time. But they thought that not all the rainfall is converted in river flow. There are some losses. So they introduced what is called the runoff coefficient, which is a reduction coefficient. The value of the runoff coefficient ranges between 0 minus or equal of C minus or equal of 1. And of course it cannot be less than 0 because the river flow cannot be negative. Okay, so all the values here are positive ones. Rainfall is positive, the area of the catchment is positive, and also the runoff coefficient is positive. That's fine. And it cannot be greater than 1 because, of course, you can't have more flow in the river than rainfall. But let me say that there are some catchments for which we observe sometimes runoff coefficients greater than 1. Let's think at a snowmelt, for instance. If you have a snowmelt contribution, you may have a flood even without rainfall. Okay? So, of course, you wouldn't use the rational formula to explain a snowmelt flood. But if you try to explain a flood originated by rain and you have even a small contribution of snowmelt, then you can get you can observe a runoff coefficient greater than 1. We assume usually that this is not reasonable from a physical point of view. So there is an hidden assumption in this formulation of the rational formula that the only contribution to river flow is given by rainfall. This is not explicitly stated usually. But if you state that the runoff coefficient is between 0 and 1, lies in the range 0, 1, then you implicitly say that you assume that the only contribution to river flow is given by rainfall. Fine. Okay, then the basic idea is simple, and you can recognize in this basic idea a concept of mass balance. Correct? Because basically you are equating the mass of rainfall to the mass of river flow here. And also you can recognize that this model is linear. Let me say that you can recognize a concept of mass balance, as I said, but still you can also say that this is a very empirical model. So this is a case in which the classification is not easy. And let me say that we don't care about it. But it's important that in your mind you elaborate the concepts. So it's important that you can recognize here the mass balance, because it means that you are not just blindly using a formula, a relationship. You are trying to understand what's going on. And this is extremely important in hydrology. So it's important that you recognize the mass balance here, but you also recognize that it's very empirical. And the fact that it's empirical is also given by the fact that it's linear. So a linear model in hydrology, I told you, it's not really fine. And let me just make a consideration which is almost philosophical. When you make design in civil engineering and you use concepts of hydrology, I told you that there is uncertainty, and I told you that we still don't understand many of the hydrological processes. So, for this reason, it is extremely important that you use experience. I already mentioned to you that experience is not proportional to the age of a person. It's just proportional to the effort that this person makes to understand what's going on. So it's extremely important when you use, when you make design and you use hydrological concepts that you don't use them blindly, but you try to understand if you are using a correct representation of the processes. So it's important, these considerations are relevant. So this is mass balance model, but still it's empirical, it's linear, so if it is linear it means that it's not really correct. These are all important considerations. So you have to get used in hydrology to, you know, to really evaluate with care what you are doing. It would be different if I was certain that this model is true. If I was sure this model is true, you have rainfall, you measure rainfall, and then you get this coefficient, which is perfectly given, and you get the peak flow. if I was sure of this model, I wouldn't say the same thing. I wouldn't tell you, you have to understand what you do, and you have to elaborate on what you do. If you are sure of the model, you just apply it. But if you realize that the model is not sure, it's uncertain, then it's extremely important that you make some personal considerations. In hydrology, remember that if you take two engineers and you give to them the same problem and the same data and the same model, and then after 2 days they come up with a completely different solution, you shouldn't be amazed. This is normal. Completely different, let me say slightly different. But if you see a difference in design variables of 30%, it's normal, which means that your interpretation is important. Now, this model, I said, is very simple, it's uncertain, but still it's very useful because it's a very smart model. Very often you have a measure of rainfall. During floods, afterwards, you always listen to people saying, yeah, the rainfall was extremely relevant, like 200 millimeters in 1 hour. So it means that rainfall is basically known. Extreme rainfall is known because we have a lot of rainfall data, and therefore this model is extremely useful. And what is the main limitation of this model? The main limitation is given by the fact that you have to estimate the runoff coefficient. And this runoff coefficient, even if the range of variability seems to be quite restricted between 0 and 1, but still you see that if you make a mistake and you assume that the runoff coefficient is 0.5, instead it is 0.6, you would say, okay, my guess was almost perfect. But if you think in percentage terms on the estimated peak flow, the difference is 20%. So between 0.5 and 0.6, there is a difference of 20%, which means that your design variables is 20% different. So it's a problem to estimate this runoff coefficient, even because it's extremely variable. There is one thing that helps us. During floods, the runoff coefficient is close to 1. And this is helpful. Why this? Because floods occur when water losses are very limited. Otherwise, I wouldn't have a flood. If the water loss was very relevant, I wouldn't have the flood. So if I'm interested in estimating the peak flow, I have to realize that the rainfall losses are very limited. And this can be explained because usually flood occurs when the catchment is very wet, so you don't have infiltration. The catchment is close to saturation, you don't have infiltration. And also the flood occurs when you have a very heavy rainfall, which is also hitting the catchment as a whole. Because if the rainfall was hitting just a small part of the catchment, you wouldn't have the flood. And therefore, the flood occurring conditions where the runoff coefficient is close to 1. So as an engineer, you could say, okay, let me be safe, and let me take this equal to 1. This is a safe option. And I have to say that very often the rational formula is used with this purpose, to get an upper value, a very safe estimate of the peak flow. I mentioned the spatial variability of rainfall because here there is an hidden assumption which means that rainfall is extended over the whole area A of the catchment. Because if you multiply rainfall times the area A, it means that you are assuming that you have rainfall over the whole catchment. This is not always true, of course, because rainfall is extremely spatially variable. But during flood, as I said, it's an assumption that is reasonable. There is to say that the fact that rainfall doesn't cover A completely is also included in the value of the runoff coefficient. So basically, the runoff coefficient doesn't take into account water losses only, but also the fact that rainfall could hit only a part of the catchment. Okay, I think we can move forward by keeping in mind this very simple but important model. And please take also into account that the rational formula is very often used. And as I said, if you have to provide a very quick and safe estimate of the peak flow, it is extremely useful. So sometimes I am asked, what is your guess on the peak flow of this river? A safe guess. I say, okay, very simple. I compute the area of the catchment, and basically it can compute it on Google Earth very quickly. And then I take the extreme rainfall on that area. We will see later how to estimate extreme rainfall, and then I just multiply the extreme rainfall times the area of the catchment. This is a very quick way of getting an upper estimate. It is very useful. Okay, but we are not really interested in peak flows. So this model, in our context, is not very useful because it's not really a rainfall runoff model. It provides an estimate of the peak flow only. Still, we can call it a rainfall runoff model, and it's considered the first hydrological model. Good. The next slides provide to you some empirical formula for the estimation of the runoff coefficient. Because, as I said, this is the key. And there you have here some indications. You find these tables, which I won't ask at the exam, absolutely, will not ask at the exam. But you find these tables on the manual for the engineer, for instance. In Italian, we have a book that is called the Manual of the Engineer. Basically, in English, I think it could be called Guidelines for Practical Engineering. And it's extremely useful for us. I think in English there is also something similar. Probably it would be called the handbook. We say manual because in Italian hand is mano. So manual is a synonym of, for us it's equivalent of handbook. So the handbook of engineers in Italian contains these tables, and you can find these tables in many books of hydrology. But it's useful. I wanted to show them to you because it's extremely useful, especially if you don't have a natural catchment, but if you have a small irrigation catchment or a small urban catchment. The rational formula, I forgot to say, it's very used in urban hydrology. You estimate the flow for sewer systems, because then it's very reliable, because urban catchments are impervious, so the runoff coefficient is very close to 1. So it's useful, and you can see here some guidelines. Okay, here the next slides are useful for you to estimate the time of concentration for a catchment. And they are empirical formulas. You don't need to learn them by memory, absolutely. I just want to tell you one thing, that there are empirical solutions for estimating the time of concentration, of a catchment. And you may say, why you are showing this slide now, soon after the rational formula? And I ask you to be patient, and you will understand why the time of concentration is much relevant to the rational form. And there are several formulations, empirical formulation for the time of concentration. I think there are 3 slides. And if you try to apply all of them to a catchment, you obtain completely different values. Unfortunately, the time of concentration, as I told you, is something that you can't measure. Is an inherent behavior of the catchment is like a parameter, and unfortunately, it's very hard to estimate it. Okay, let me move forward. Other model, time area method, in Italian it's called modello della corrivazione. And it's also called, in Italian, modello cinematico. But this is unfortunate because in Italian and in hydrology we have two different modello cinematico which do completely different things. They refer to completely different context. So I prefer when I teach in Italian to call it modello della correlazione. And in Italian correlazione is concentration. So you can also see an association between this model and the time of concentration. But anyway, let's refer to the English language, which is clearer, time area method. So, it's a very simple model, and it's based, first of all, let's refer to a catchment. And it's based on it's based on assuming that you can compute the time it takes a drop of water to travel from each point in the catchment to the closure section. So let's suppose that you can compute this time, the time that each drop of rainfall takes to move over the catchment without infiltrating to reach the closure. And you know that the maximum value of this time for the catchment is the time of concentration. So again, let's suppose that wherever in the catchment where you are, you can compute the time that the drop of water takes to reach the closure. And again, let me remind you that the maximum time for the whole catchment taken by this drop of rainfall to travel to the closure is the time of concentration. So basically, if you can compute this time, you can draw over a map of the catchment the so-called isochrone lines, which are given by the points that